All right. Good morning, everyone. Thanks for joining for today's CGD seminar. Before we get started, I'll remind everyone of our Cgd Code of Conduct, these seminars, where we offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. I'll also ask that everyone please keep themselves muted throughout the talk, and please hold any questions until the end, except for any clarifying questions. Now it's my pleasure to introduce today's speaker, our own Keith Lindsay, who is a Project Scientist 3 in the Oceanography section here in CGD. He received a bachelor's from Virginia Tech and a master's and PhD from the University of Michigan in mathematics. His expertise and interests include ocean biogeochemical modeling, the global carbon cycle, and ocean modeling, particularly tracer transport. He's co-chair of the Biogeochemistry Working Group and the 2019 recipient of the CESM Distinguished Achievement Award for his leading role in implementing an interactive carbon cycle in CESM. Today, he'll be speaking about the application of a Newton-Krylov solver to spin up ocean tracers. So Keith, take it away. Feel free to share your screen.
Thank you, Dan. I'm clicking the buttons. And how does that look?
Looks good.
Thanks for the introduction. And as Dan said, I'm going to be talking about the application of a Newton-Krylov solver to spin up ocean tracers. Before I get into the material, I'd like to give a hearty thank you to my wonderful collaborators and colleagues that have helped me on this and related work over the years. On that top row is Francois Primo and Ann Barden at the University of California at Irvine. I've worked quite a bit with them on Newton-Krylov work. And in the bottom row, Matt Long and Frank Bryan at NCAR have offered lots of helpful advice over the years on this work. And more recently, Andrew Shao in the bottom right has helped a lot with the transition of this work to the MOM6 ocean model. So thank you to these wonderful collaborators and colleagues. It's great to work with good people. So I'm going to give a little bit of background here on one of the reasons that I'm looking at this work. In one of the applications of spinning up these ocean tracers is a project that I've been doing with the Community Earth System model for many years, is coupled climate carbon cycle modeling and initializing these models. And one of the challenges when you are coupling carbon pools from different components to each other and doing this in a conservative way, the net carbon in the system is conserved. And so because the carbon pools are coupled this way, drift in the ocean model doesn't stay in the ocean model. This is not Las Vegas. So we want to have a drift-free run so that we don't have drift from one component affecting the other. And we've dealt with this as we've done this coupled climate carbon cycle modeling in different versions of CSM, CCSM, and now CESM. We've taken different approaches over the years to have a spun up ocean carbon cycle model. And I'm just going to highlight how that has evolved over the years. In our early iterations of this, we ran the BGC at a low resolution compared to what the typical climate resolution was run at. And so this helped a lot with being able to do a spin up because the model was cheaper. And we also used what's known to as a depth dependent acceleration. So when we're doing the ocean model takes longer time steps at depth than it does in the surface. And we ran that model for 350 surface years, and we're accelerating the deep. So that was over 10,000 years in the deep. And so this spun up pretty well. However, this depth-dependent acceleration leads to non-conservation of tracers as tracers cross the layers where you have a change in that depth-dependent acceleration. And we had to put in some ad hoc fixers to correct for the non-conservation of this acceleration factor. Stepping forward a handful of years to a newer version of the model, CCSM3, where we undertook more coupled climate carbon cycle modeling. We again used low resolution models. In this case, we just ran the ocean model for 1,000 years, and we did not apply the depth-dependent acceleration, primarily because we were doing this experiment with a full ecosystem model, and the fixers get much, much more complicated when you have different constituents that are being not conserved. It's hard to generalize the ad hoc stuff that we had done previously to the more complicated full-blown tracer package that we were using in CCSM3. So we ran for 1,000 years and lived with the drift. Stepping forward a bit more to CESM1 is basically the same kind of thing, that we did not use that depth-dependent acceleration. And now we're running the model at the same sort of resolution that the climate model is being run at. These are the zonal resolutions of the that I'm listing there are the zonal resolutions of the atmosphere in the ocean models. And so we ran the ocean model again for 1,000 years. It's much more expensive now with the higher resolution model. And we did a little tweak in our ocean spin up to help reduce outgassing. So we kind of cheated a bit with our spin up by changing our parameters near the end of our spin up. As we moved forward towards CESM2, things were, in the meantime, we were trying to develop techniques to spin it up besides this brute force. And one of the things that emerged in the literature were these Newton-Krylov solvers that I'm going to talk about that were published in Ocean Modeling for Offline Tracer Modeling in 2008 by Lee and Primo at Irvine in Cadwalla, who was at Columbia at the time. So before going further, I want to explain with words and then with equations what I mean by the ocean spin-up problem. So the statement of the ocean spin-up problem from a verbal point of view is we want to generate tracer distributions or spatial patterns that are in balance with respect to the ocean model circulation. Note that this is an ocean model circulation that is time varying. So you have a seasonal cycle of mixed layer depths, you have a seasonal cycle of circulation, and you also have high frequency variability of circulation throughout the range of the ocean model. There are many applications for doing this. One that I talked about in the previous slides is initializing transient experiments. Another is just to be able to cleanly analyze the dynamics and properties of spun up tracers. If your tracers are drifting and you have nonlinear dynamics between those tracers, then you might not be seeing the nonlinear interactions between them with drifting tracers. That is, the nonlinearities might evolve over time as the tracers spin up. And you want to know, well, what is the final state of the model if we were going to make conclusions about how your model behaves. If you want to compare your tracers to observations, you want to be doing that without having drift present in your observations. And more on a deeper level, if you want to then optimize some parameters in your model to reduce bias compared to those observations, you need to be able to spin up repeatedly. So this means that spin up has to be feasible to do regularly if you want to get into this, if you want to get to doing the optimization of model parameters. And a challenge here is that running brute force ocean model spin up is prohibitively expensive, both from a wall clock time point of view and from a computing allocation point of view. We only have limited allocations of computer time, and we only have limited number of days in the year. So for example, if you want to do a brute force spin up of 2,000 years, and if you have a model that runs at 50 years per day, which is sort of a typical amount of performance for the GCMs that we run at the climate scale, that takes you over a month to do a spin up. So that is not something that you can do regularly. And it's also not something that you can do repeatedly to optimize parameters. So there's a challenge. As Dan mentioned, my background is mathematics, so I'm going to restate what I just said from a mathematical point of view to put it down to, then you can use math to make progress on solving these equations. So I'm going to introduce some notation here. C of t is just going to be a vector denoting the tracer state in the ocean model. So these are tracer concentrations. For a typical climate model configuration, like with our POP 1 degree model, we have around 4 million grid points in the ocean model. And with one tracer on our newer ocean model, MOM, on our 2/3 degree, we have an order 10 million grid points in the ocean model. So these are vectors in 4 million or 11 million, 10 million dimensional space. So it's a high dimensional space. I'm going to introduce the notation that the forward model operator that takes an initial state C0 and maps it forward time t, I'm going to refer to that as phi. And this is just some shorthand notation so that the equations, we can then put stuff into an equation form later. But this phi incorporates all aspects of the GCM, advection, mixing, surface fluxes, interior source sink terms of reactive species, etc. The mathematical formulation of the spin-up problem is that we want to find a particular initial state, C star, such that if you run the model forward from that initial state time t, you get back to the original state, C star. So this is, the tracer end state is the same as the tracer initial state. And you would typically take this capital T to be a period of a forcing or circulation over which you are spinning up your tracers with respect to. So you might do this over a 10-year period of forcing that includes for maybe El Nino events and La Nina events, so that it's long enough to have some sort of representative climate to it, but not too long for reasons that we'll talk about later. This equation of phi of C star equals C star, we're going to rewrite that with a new function that I'm introducing, capital G, which is the end state minus the beginning state. And now we're trying to find C star such that this equation is 0. And now we've got an equation that we're trying to solve for 0, and we can use math to work towards solutions of that equation. The particular mathematical technique that we're using to solve this system of equations, so as a reminder, this is a system of equations with many millions of unknowns. We're going to use Newton's method. And you might have learned about Newton's method in math class many years ago. In one-dimensional situations where you look at a tangent line and find the solution of a tangent line to a curve, and then you do this iteratively until you iteratively converge to your root of a function. And this works also in higher dimensional situations that we are in. So this is generating a sequence of state vectors, C1, CK, et cetera, that will converge to the solution of equations. And the way that Newton's method is derived is that we say that we're going to approximately say that the function that we're solving for at the next iterate is equal to 0. And then we do a Taylor series expansion where we expand about the current iterate, CK. And the Taylor series expansion is that this G of CK plus 1 is G of CK plus a Jacobian matrix times a difference of your state vectors. If you rearrange it, and we ignore higher order terms in Newton's method. If you rearrange this and solve for CK plus 1, you get this equation for CK plus 1. And this Newton's method converges very rapidly, but we're going to find that some of the stuff that we do in the subsequent steps will reduce that performance that we get with Newton's method, but it still converges well. In order to compute that increment in Newton's method, we need to evaluate this matrix inversion times a state vector. And that is not straightforward to do. Oops, I skipped too far ahead. Because that matrix is, it's a dense, large matrix that we cannot store or compute all of the terms to it. So it's order millions by millions. So it's impractical to use direct methods to solve that linear system of equations. But what we can do with that matrix is that we can do matrix vector products with the matrix. And the way that we do that is that the matrix times a vector, which we think of as an increment in tracer, that this is a forward difference, a finite difference approximation to doing this matrix vector problem. So if you think of the derivative is equal to dy over dx, then if you multiply that by dx, you get dy from a 1D point of view. And mathematically, then this is the same as saying that we're taking g with this perturbed initial state, subtracting it from g of the original state, and then there's this scaling factor so that we are taking infinitesimal increments. So this finite difference approximation allows us to do approximations to these matrix vector products. I'll point out here that computing this matrix vector product involves computing this g term here on the first term on the right-hand side, and evaluating that is a forward model run of length t. So every time we're doing iterations in these iterative methods where we're needing to do these matrix vector multiplies, we need to do a model run of length t. And so that leads us to wanting t to be not too big, because otherwise every iteration would take longer to do. So for better performance, we want t to be small, but to have representative circulation, we want t to be large. In those, there's a tension between there and finding a decent optimal value. Given that we can do this matrix vector product, there's a class of iterative methods called Krylov iterative methods that can solve these linear systems of equations in this situation. So we're going to now jump to Krylov methods. So we're using Krylov methods to solve this system of equations for the increment in Newton's method. And what the Krylov methods do is it's an iterative method itself, because we're not doing direct methods to solve these equations. Every iteration of GMRes, this Krylov method, evaluates a matrix vector product. And when it does so, it constructs what is referred to as a Krylov basis. This is named after the original researcher of the Russian mathematician Krylov, who first researched these methods. And from this Krylov basis, which is built up by sequentially multiplying your current vector by the matrix, doing these matrix vector products, we look for a linear combination of these vectors produced in the Krylov basis and refer to that as X. And we want the linear combination that minimizes the residual from the linear system of equations that we're trying to solve. So we're looking for matrix times X plus the right-hand side, and we're looking for X that minimizes that. And GMRes does the math to find the optimal linear combination of these basis vectors that minimizes this residual. If that was the end of the story, you'd be off to the races. But GMRes usually does not work well if you do not use what is referred to as a preconditioner. The equations that we are dealing with are poorly conditioned from a mathematical point of view. And so we introduce a preconditioner to regularize the system of equations and increase the convergence rate of the Krylov method. So we take this system of equations that we're solving with the Krylov method, and we multiply both sides of the equation by a preconditioner matrix, P. And for P to improve convergence, you want it to be an approximation to the true inverse of this matrix. Again, this is not something we can compute, but we want this to be approximately true. But we also need to be able to multiply by P in an efficient manner. And so there's some tension here in developing a preconditioner that has that brings about the properties of the matrix that you're trying to invert, but you can invert it in a reasonable way or apply it in a reasonable way. In this work, we're going to use a preconditioner whose derivation was laid out by Lee and Primo and Kadawala in those papers that I mentioned previously. In applying the P that they developed, a framework for deriving, involves inverting a large sparse matrix. This is in contrast to G, which has a dense matrix. So we invert a sparse matrix, which is doable with appropriate software libraries. And we use a particular library that is parallel called SuperLU, developed by Lawrence Berkeley Labs. The particular preconditioner approach that Lee and Primo and Kadawala developed ends up requiring the matrix entries that are of the form the derivative of a tracer tendency with respect to the tracer itself for the different tendency terms in the GCM. So we want to know what is the derivative of an advective tendency with respect to the tracer. And so this is telling you something about the model's operators, the advective, diffusive, lateral diffusion, and vertical mixing, and for things with source sink terms, the derivatives of the reaction terms with respect to the tracers. We get these diagnostics for the sparse matrix that we invert with SuperLU in practice by using a newly developed impulse response function tracer module that we insert into the GCM. So the way this works is you put the tracer in the impulse response function to an impulse every time step. And then you run through the normal model execution to get the advective, lateral mixing, vertical mixing terms. And we get that tendency from that impulse, and then we reset, and then we take the time mean of that tendency. And because it's an impulse, that gives us what we can approximate the derivative of the tendency with respect to the tracer. And we need to reset that tracer to the impulse every time step. There's some cleverness where if you had just put impulses all over the globe, and for every point on the globe, if you had a tracer that represented an impulse at that location on the globe, you would have the number of tracers would be equal to the number of grid points on the globe, which would be hundreds of thousands, which is not practical to run with. So one of the ideas of Kadawala and Lee and Primo was that you can superimpose these impulses if their tendencies do not overlap with each other, and you can reconstruct the tendencies from the individual impulses from a single tracer for multiple impulses. It turns out that if you superimpose these in a clever way, you can represent the full domain with relatively few tracers. And this gets into a neat application of graph coloring algorithms to minimize that IRF tracer count. And so this is showing what happens if you apply one of those algorithms and zoom in to the MOM 2/3 degree. It turns out that the MOM 2/3 degree grid with the periodic boundary condition zonally in the seam on the northern boundary condition, you can color that with 11 different tracers instead of hundreds of thousands of tracers. So here, each color represents an IRF tracer and represents a impulse at that location for that number tracer. using tracers numbers 1 through 11. And there's a touch of irony that I'm showing this plot as a colorblind person. This is not actually a color blindness test, though it does kind of look like one. Putting this all together, we're solving the system of equations for spin-up. G equals 0. The tracer end state is the same as the initial state. We're using Newton's method, which I've rewritten here, the equation, an iterative method to solve this equation. The increment in Newton's method is computed using a nested iterative method, GMRes. And inside GMRes is a model run. So as it gets kind of complicated to put all of these details together in a scripting system where inside this double nested loop, you want to submit a batch job to the supercomputer and get the response and get the results back to do that forward model run, and then resume the computation inside that nested loop. And so there are off-the-shelf packages for doing Newton-Krylov methods, but they don't work well with this environment of where you need to go wait for a long execution time to evaluate your function of doing this forward model run. So a lot of this I had to roll on my own. And I'm omitting a bunch of technical details here, the derivation of the preconditioner, some optimizations that you can get from running the solver simultaneously on uncoupled tracers, if you want to spin up radiocarbon and age simultaneously, for instance, and the scripting challenges. But we were able to overcome that with earlier versions of CESM and get some decent results. So this is some results that I published in 2017 in the Ocean Modeling Journal, applying this Newton-Krylov technology framework to the ideal age tracer in POP. This was running at our 1 degree resolution with 60 layers, that sort of 4 million grid point configuration. And this is a forced simulation. And what this plot is showing is the RMS change in ideal age as the Newton iteration increases. So we're getting an exponential convergence. Our residuals are going down exponentially. This is a logarithmic plot. So after 10 iterations, the RMS in the tracer, is 10 to the minus 4 years per year. So it's converging really, really well. And to have equivalent convergence with the brute force method would take orders of magnitude more computer time than we're able to do with the Newton-Krylov method. Those are some published results applying the technique to ideal age. And sort of the timeline of how progress on this Newton-Krylov solver framework has proceeded. In 2009, there was some initial success with ideal age at a 3 degree model, which is what we were running BGC with in the early days. And there was some modest success for BGC at that low resolution, but trying to transition that to the by one failed. We weren't able to get that to work. And as we were trying to do this development of this technique, while the model development is going from these different versions of CESM, it just became clear that it was going to be too late to have this working for BGC for CESM1. And that's why we did brute force spin up for the CESM1 initialization. Some years later, I finally managed to get success for the Newton-Krylov technique for the by one resolution with the simple tracer of ideal age. Unfortunately, the complications of the BGC the success of the solver did not translate to the more complicated BGC tracers with the by one. It turns out that some of the BGC updates that we had in subsequent models releases broke the success that we had in earlier versions. So we weren't able to get the pieces together in time for CESM1 or CESM2 completely. That said, there were some other successes along the way of spinning up radiocarbon for different model configurations like the LGM. It's been used to spin up noble gases that are useful as a diagnostic of ocean ventilation, and helium isotopes, which are a useful diagnostic of evaluating deep ocean circulation. Another notable thing about these other successes is that all of these successes of the solver were done by people besides me. That the goal of this project is to produce a tool that other people can use to enable more science for them, and not just me doing it for the BGC working group success. We want it to be a tool that other people can use for their own science. And so there was some success along the way of having other people use the tool that had been developed. That said, as we were progressing towards CESM2, it became clear that the development of the solver had not progressed enough to get success for applying it for the full-blown BGC in CESM2. So we developed an idea to, instead of trying to use Newton-Krylov to spin up the full BGC suite, was to target a subsuite of the BGC tracers. And because we couple carbon in the ocean model to the rest of the system in this coupled carbon climate framework that we're talking about that I referred to on the very first slide, it's really important to have that spun up. You want to prioritize having the carbon pool spun up over, say, the nutrient pools or the oxygen pools. If you can't do them all, focus on carbon. And carbon is also a little bit easier than nutrients and oxygen because the nutrients have nonlinear feedbacks and oxygen has some complications with oxygen sink terms, have a nonlinear dependence on oxygen concentration. So that makes them more complicated for the Newton-Krylov solver. So carbon's easier and it's more important. So we focused on carbon. That said, it's not totally easy. There are some nonlinearities with the carbonate system. And for instance, the burial of sinking calcium carbonate at the seafloor has some nonlinear interactions with the carbonate chemistry that the model is generating, that if things are acidic enough, the calcium carbonate there's dissolution into the seawater column, whereas things are not that acidic, then that calcium carbonate gets buried. So there's some nonlinear feedbacks present that you need to deal with. That said, we were able to deal with those nonlinear feedbacks for the carbon system. And we were able to use Newton-Krylov generated initial conditions for CESM2 for the carbon pools in the ocean. And we were able to get very small drifts. If you're a carbon cycle modeler, you'll know that this 0.2 drifts of petagram per year is a well-converged metric for the carbon system. And so here are a couple of diagrams showing some of the progress of as we were doing the spin-ups of the tracers, applying the Newton-Krylov method to some tracers and not the others. This is a little bit of a complicated picture, I admit, but this first curve, this black one, in both of these figures, so here we're looking at carbon and age in the deep North Pacific. The black line was our first attempt at a spin-up for CESM1, and we had a lot of drift going on. And at some point, we realized that it was really a lot of drift, for instance, in oxygen, and oxygen was going to zero in wide swaths of the ocean. So we had to step back and do some modifications to the BGC tuning to compensate for weak ventilation of the deep Pacific that was evident in our long spin-up runs. By the way, these are model years on the horizontal axis. So we ended up doing a series of experiments where we were retuning ocean BGC. And then at points as we were doing experiments, we would apply the Newton-Krylov solver to the subset of the tracers. And that's why we have jumps in these tracers where the Newton-Krylov is applied to the carbon tracer, but not to all tracers, for instance, not to oxygen. And then you can see this, when the Newton-Krylov is applied, the drift goes away. And what we eventually initialized our model with was the end state of this experiment number 32. So you can see that over the last few hundred years, There's very little drift in experiment number 32 for carbon. In age was also very little drift in age compared to what we saw with the initial run without Newton-Krylov. Now, if you're familiar with the circulation of the ocean, you'll know that 4,000 years old is very, very old for the deep Pacific. Radiocarbon age measured in the ocean is under 2,000 years old. So this is an indication that the ocean circulation is too weak to ventilate the deep Pacific. And this led to needing to retune our ocean BGC. And we did not realize this until the ocean physics was frozen for CESM2. And so this is something that I'm going to get back to in the later parts of the talk, is that if we had applied Newton-Krylov to age with that ocean circulation, we would have perhaps realized earlier in the game that the ocean circulation being generated by CESM2 was too anemic, and perhaps we could have lobbied to have some physics changes to improve the deep ocean's ventilation, but we didn't know how bad it was. And we got into a bit of a bind as we were doing BGC development for CESM2 because this deficiency in the model snuck up on us. Back to Newton-Krylov. Newton-Krylov was working for the simple tracers like ideal age and radiocarbon and the dyes and the helium isotopes in carbon. And there are challenges with applying it to more complicated tracers. And some of the scientific reasons why this is complicated are that these tracers have dynamics on timescales that are days or shorter, much longer than the time integration length that we're applying Newton's method to. And so the nonlinearities that you have in these tracers have timescales that the linearization of Newton's method does not see these nonlinearities. And so this makes it complicated to apply the linearization of Newton's method to these tracers. There's a framework for using what I refer to as shadow tracers that I'll describe in a couple slides that helps deal with that problem. Another challenge with non-simple tracers is that having conserved quantities, for instance, if you have if your model is conserving total carbon or total phosphorus or total silicate, which it ought to do, this leads to a singularity in the matrix that you're inverting for the Newton increment, and you need to have some ways of dealing with that. And there's also complications where you have, if you have jump-like discontinuities, for instance, if oxygen consumption drops off when oxygen concentrations are low, these, what look like discontinuities to the Newton-Krylov solver can lead to overshoots in poor Newton-Krylov conversions. These are some of the reasons why applying the technique to the BGC tracers wasn't working well when we transitioned from the simple tracers to the non-simple tracers. And generalizing the solver to deal with these complications was hard to do with the GCM because it's a big system to run and experiment with ideas to deal with these scientific problems. And so it became clear that it was time for a new implementation of the Newton-Krylov framework. And there were identified a number of issues and shortcomings with the initial Newton-Krylov solver that were making it hard to do this new development work that was needed to work on the BGC tracers. One of the challenges was that there's POP-specific tracer details littered across the scripts. It made it hard to experiment with these ideas to enhancing the solver. There was this top-level driver that stayed in memory while I would call a model simulation, and it would wait in memory until the model ran. And when the model ran, the top-level program would restart. In the HPC batch environment that we have at NCAR, I was able to get exemptions to run long-running processes for the solver, but if we're trying to have general users run the solver, having a top-level driver persist in memory is not something that we can really have going on. Another complication with the initial solver implementation was that it was written as a combination of shell scripts and the NCL framework developed at NCAR, And that made it complicated to share data between the different environments, like the variable names that you're dealing with, having it reproduced in the different frameworks of the shell scripts or the NCL scripts. So having a new framework that can deal with all of these issues was what we wanted with a new implementation. So that we made a new implementation a few years ago. It was implemented in Python, facilitating file manipulation and data processing in a single environment to reduce the duplication of data in different environments. The solver has a restart-like capability, so you can exit and resume later where it exited. So the solver doesn't need to persist in memory. So this means that you don't have to have this single long-term running master process. It's generalized to work. The Newton's method doesn't have stuff about our ocean model embedded in it. It's just an abstract Newton's method and an abstract Krylov method applied to a Python class that I referred to as model state. And then all of the pop details get isolated into a subclass of models, a pop specific subclass of model state. So all the tracer names that are particular to pop or the restart file conventions of pop go into this subclass. This is using the object-oriented features of Python, something that NCL didn't have. And once we had this framework of a object-oriented nature of Python that we're applying Newton's method to, we could then apply the same scripts to simple models, like a 1D model with time variation or a 2D model with circulation, and then apply ideas to the solver to these 1D and 2D simple model formulations, instead of needing to run the full-blown GCM every time you want to try out a new idea. What we're able to do with this new framework is implement a shadow tracer approach. And this is what I referred to briefly previously, that where we have these ecosystem variables that vary non-linearly on these short time scales, like primary productivity consumes nutrients in weeks compared to the many years that we're integrating the model over. The way that we can apply the Newton-Krylov to these tracers is we can apply the Newton-Krylov system solver to the system without these nonlinearities. And what we can do is do a short run to spin up the ocean's biological pump that generates source sink terms for things like nutrients and oxygen. Then apply the Newton-Krylov to spin up nutrients and oxygens with the biological pump from that first step. And when you're doing that, we're not changing the biological pump. So we're using a fixed biological pump and spinning up the tracers with respect to that fixed biological pump. And then we iterate. And once we have spun up nutrients, we respin up the biological pump and we iterate this. So this is another iteration in our nested iterations. So in words, this is running a prescribed biological pump using shadow tracers, and the shadow tracers do not feed back to the biological pump. One of the challenges with this is that the biological pump is then uncoupled from the shadow nutrients, which means they do not have the negative feedbacks that are present in things like our primary productivity formulations. And so the tracers can go negative if there's no feedback to down-regulate the biological pump. And so you require some experimentation to deal with techniques in the solver to deal with this. And that's doable in this 1D framework. So this is showing an example from a 1D phosphorus model in this simplified solver framework with a simplified restoring of the shadow tracer of phosphorus to a real tracer. And this is showing that it converges exponentially, and with 5 iterations of Newton's method, we have reduced our residual 3 orders of magnitude, which is sounding like it's doing very well. But with the 1D framework in this, where you can try out new ideas, you can try out another idea where instead of just having a fixed restoring timescale of your shadow tracer, what if you try something that's more physically motivated, where it mimics the dynamics of uptake and primary productivity? If I use a more sophisticated restoring timescale formulation, now in 3 Newton iterations, the residuals have gone down 7 orders of magnitude. So with this 1D framework that the solver can run on, I can do these experiments on my laptop in a day instead of trying out different ideas on the GCM that takes many days to do. This can also be applied to 2-dimensional configurations that are implemented with this simplified framework. So here now I have I'm showing a stream function represents a 2D test bed of advection, diffusion, reaction. So there's some circulation that the stream function is representing. This red line is showing a boundary layer depth at one end of the basin that can vary in time from it can shoal up to the near surface, or in different parts of the year go down to the depths. And by having this time varying circulation, this mimics some aspects of our 3D GCM. But we can run it, I can run this on my laptop in 30 seconds, 1 model year. I've implemented an oxygen-like tracer that we were having problems with in the full-blown GCM. And this is a tracer that has some sort of a gas flux-like boundary condition at the surface. And there's production and consumption of oxygen that comes from a 2-dimensional phosphate model. And then if oxygen gets close to 0, the consumption is downscaled, having the same sort of nonlinearity that we have in the full-blown GCM. So this oxygen tracer has something that resembles an oxygen minimum zone that causes problems for the solver in the GCM. And indeed, if you apply the Newton-Krylov solver, sort of just vanilla, to this tracer, it doesn't converge. You get non-physical values, and the oxygen oscillates from Newton iteration to Newton iteration around 0. With this simple framework, you can then start trying, well, what if I have ideas of how I can deal with non-physical values of our tracer? And what if I put in an idea to enforce physically based bounds on our tracers coming out of the Newton solver? And if you do that in the 2D problem, indeed now, with 4 Newton iterations, the residuals for the oxygen tracer have gone down 5 orders of magnitude. So it's not quite as good as the simple tracers. The limiters of enforcing the bounds are reducing the convergence rate, but we're converging. Whereas if you don't enforce these physical limits on the tracer with oxygen in this framework, it doesn't converge. So this framework of having this Python-based solver allows experimentation of ideas for the solver. So there's some ongoing projects for the solver. One is to apply the techniques that I just mentioned from the 1D and 2D BGC models to the full-blown 3D marble model. So that's the shadow tracer approaches, and for nutrient source sink terms, and the limits for tracers like oxygen. We want to apply those to the full-blown 3D marble so that we can spin up the full-blown BGC tracers. We also want to be able to do this for the carbon isotopes in marble. And one of the challenges with doing this is needing to deal with co-limiting nutrients that complicates the application of what was developed in 1D. Another ongoing project is applying this to the active tracers, temperature and salinity, perhaps using the shadow tracer approach. Another project that's going on is transferring all of this work to the MOM6 GCM that we are transitioning to in CESM, so that we can spin up our tracers with MOM6. Having the solver be generalized to deal with arbitrary systems eases that transition from the solver from POP to MOM6. And there's also a project to apply this to the carbon and nitrogen pools in CLM and CTSM. There's some initial conversations with the CLM developers on doing this project. Now, all of these projects are full-time research projects, and so I can't do all of them. We can't do them all simultaneously, and so we need to prioritize them. And one of the things that I referred to earlier is that as we were doing the development of CESM2 with BGC, we really got in a bind because the weakness of the ventilation in the deep Pacific caught us off guard. And so when that happened, one of the things that we said to ourselves is, we don't want that to ever happen again. We don't want to be caught trying to spin up BGC and find out that the circulation is really, really off. And so because we not wanting to relive that experience, research is focused on applying the solver to MOM6. And that has a number of challenges that I'm going to highlight here, and then I'm going to give an update on how this implementation is going. And that will be the remainder of my talk. Even just evaluating this functional form that this function that we're trying to find the zero of this end state minus the beginning state, one of the features of MOM6 is that it has a time varying vertical coordinate. And so just even interpreting what this means spatially, when you run the model forward in time, n years, this is on a different vertical grid than this other term here. In order for that difference to make sense, you want to compute that difference on a common vertical grid. And so the ultimate goal with the MOM6 implementation of Newton-Krylov is to evaluate this difference on a fixed z-star coordinate, instead of whereas MOM can run with z-star coordinate, which is a slightly stretched z coordinate or a hybrid coordinate. But if we're running the Newton-Krylov solver on a fixed z-star coordinate, then this difference makes sense. Where there's a mismatch between this z-star coordinate, so the idea is initialize tracers on the z-star coordinate, interpolate them to the model vertical coordinate, run the model, and then interpolate them back to the z-star coordinate at the end of the model run, and there you can take that difference. And you can apply Newton's Krylov to that difference. If there's a mismatch between the z-star coordinate and the MOM6 vertical coordinate, this effectively broadens the computational stencil width on the z-star coordinate. And this makes it hard to avoid overlap of the impulse response function tracers that I mentioned. And so there's a computational challenge of having the tracers reduce the number of tracers you need, but not have the computational stencils overlap with each other. So we're trying to avoid needing to run with hundreds of IRF tracers, which would be infeasible. This happens because of a mismatch between the z-star coordinate and the vertical coordinate native to MOM. It also happens with the neutral diffusion operator of MOM that is used for lateral mixing, because this operator can mix from one column to the neighboring column at any layer in the model. And this has a wide stencil, and this complicates some aspects of running with MOM. That said, the status of the application to MOM6 is a lot of stuff is in hand. There's an initial implementation of the subclass of the model state. Basically, I started with the seam pop subclass and changed as needed. So that's the good news. The bad news is it needs some cleanup and refactoring. Right now, there's sort of a crude implementation in hand, and it needs to be cleaned up. The IRF tracer module hasn't been implemented in MOM6, and the graph coloring tools approaches have been used to create tracers with that color blindness like map that I showed earlier. That's the good news with the IRF tracer module implementation in MOM6. The bad news is there's some of the diagnostic output specification is done by hand. That needs to be automated so that this will be more easily usable by other people down the road. And there's some ideas of doing that have had conversations with the software engineers. The preconditioner matrix generation tool has been extended to handle this output. Oops. That's the good news. The bad news is there's a lot of overlap, and this is implemented in the C programming language, and a Python implementation of this would be much cleaner. It's some pretty hairy code that you wouldn't want to show to other people, to your friends. Initial attempts at using this NK framework while all these pieces in place, applying it to the ideal age tracer in MOM, the results are not converging. which is disappointing. I was hoping to be able to show you some lovely convergence plots in this presentation, but that did not come together. And the current hypothesis is that the stencils and the IRF tracers are overlapping, and there's a misrepresentation of the model operators in the preconditioner that's mucking up the convergence rate. And there's some active conversations with some of the MOM developers, particularly Andrew Shao, to get how we can get sufficient diagnostic output to represent the model operators and do so in a way that it's feasible to run the model. It doesn't help if if you can get the right output, but it takes you months to get the output. So we need to have there's this tension of getting appropriate model output without becoming unreasonable to run the model. And with that, I will go back to just listing. I'll be happy to take questions and be happy. I'm listing what the ongoing projects are as I take your questions and answers, your questions and my answers. And thank you for your time.
Excellent. Thank you so much, Keith, for sharing your work. We have a couple minutes now for questions. So I'd invite people to go ahead and raise your hand or type a question in the chat for Keith. Peter.
So Keith, I'm wondering whether you've made any progress on the active tracer's temperature and salinity, because that would enable us to know the equilibrium ocean solutions for our ocean parameters. That would be extremely helpful.
There has been some there have been plans put in place of how to proceed, but I focused my efforts more initially on the MOM work as opposed to implementing those ideas for temperature and salinity. So at this point, there are a list of steps to be done, but they have not been taken. I agree completely that it would be very useful to have this in hand. I think all of these ideas on this ongoing project would be very useful to have in hand for us and the community.
Are there extra difficulties with TNS over, say, carbon?
Because they couple back to the flow field by changing the density structure, that adds a complication. And so the idea is I'm mentioning using this shadow tracer approach to turn off that coupling, but then you have this challenge of keeping the shadow tracers from going off the rails. So the shadow tracers avoids the problem of coupling the active tracers to the flow field, but then you need to make sure that your shadow tracers that you're applying Newton Krylov to don't go off the rails, and that can be tricky. And I don't right now have this in the simplified model where it's easy to test ideas out. So I think what it might be useful is to try to get this in the simple model where I can then try these ideas.
All right, Frank.
Yeah, Keith, I was wondering, I mean, the IRF idea for evaluating the Jacobians goes back to Kadawala and Francois. Are there any other ideas out there for efficiently evaluating the Jacobians other than the IRFs that might be more suitable with MOM 6?
I've been having conversations recently with Andrew Shao about that, and it's using IRF tracers with new diagnostics. So it's still IRF based to get the Jacobian, but trying to get not just the tendencies, but try to get the Jacobian with more enhanced diagnostics in conjunction with the IRF tracers. So I'm not sure that we would avoid completely the IRF tracers, but I think what we're talking about doing or attempting to do is not just use the existing diagnostics framework for tracers, but augment it with additional tracers that would be particularly useful for the Jacobian approximation.
Thanks.
All right, well, we're at 12 o'clock. So thanks again.